one with the larger chip. Part of the reason is if we do something and you damage the board, it's a lot less expensive to have to just buy the chip and replace it than to replace the board completely. Now this cost from them, without tax, $23. So I have an alternative supply that we can use. Let me get the URL for that. And I don't get any money or anything. It's not like this is an affiliate link or anything. It's not. And again, I'll post this so that you can find it. Amazon sells an ASCII Uno R3 board. It contains the Atmega 328P, which is the chip that we're going to be studying at the end of the semester. And it includes the necessary USB cable. You need a USB cable that has a male A on one end and a male B on the other end. By male, it simply means that it has a pin-looking thing. The A end is what you would normally think of on a flash drive or something like that. It's just a flat, kind of rectangular-looking connector. The other end looks a little bit like a doghouse. It's kind of square, and it plugs into the Arduino. I don't know if that picture shows the port. Yeah, it looks like there's the female port on the board right there. I can't point at it without losing it. But you need that cable. So if you buy it from here, you additionally need to buy a cable on top of it. So it'd be $23 plus the cost of the cable. If you buy it on our Amazon and you buy the ASCII, it's $12.98 for both. Notice I bought this the last 6 times I've taught the class. So I know it works. I know it's a good one. I wouldn't be buying it if it was junk. Now, if you go to Amazon and you find one on Amazon that costs $3, I guarantee it's junk. Don't buy it. If you find anything made by some other company other than ASCII or the original, or you could probably find a similar one at Adafruit, which is a company in New York. It's a little more expensive. Or you could find one at SparkFun, which is a California company. I would suggest not buying those. The shipping is expensive, and they also may not have the same chip we want exactly. We need exactly this chip, the Atmega 328P, in the DIP package, dual inline package. So I'll post these so you can start buying these. You don't need them this week or next. You'll need them certainly by a midterm, but you'll want to get on getting that. It'll be the only supplies you by necessity need. I will give you a couple other suggestions for things. One of the things you'll probably want to acquire, because it makes life simpler for you, is a grocery store calculator. A grocery store calculator is simply one of those cheap calculators that has addition, subtraction, multiplication, and division on it. That way you won't be tempted to try to do some of the things like convert between binary and hexadecimal, or convert to ASCII, or do various things like that. You won't be tempted to do those on a calculator, because some of the exams may or may not allow you to use them. And you need to really learn how to do them, because part of what you're doing in this class is learning to appreciate computer science at its finest. This isn't making web pages. This is talking about the science of computers. And in this, we're doing it from a practical point of view, where we not only learn the theoretical computer science pieces, but we learn the electrical, and we learn the processor type of way of looking at this thing. You'll find at the end of this, you'll go back and you go, wow, that was a really good class. I've had students from Rutgers and NJIT who've told me after they've had the follow-on class to this, that their follow-on class was really easy because everything they talked about in that class at the four-year school, we had done. So you want to keep that as one of the things in your mind, as you're really learning some good stuff here. It's not because I'm teaching you, it's because the material is really, really good. And so you want to, really take good notes, and you want to make sure that you pay a lot of attention to what we're doing. How do I evaluate you? Well, we got exams and a final exam, which is going to count about 50% of your grade. Now, let me tell you one thing. I know it's easy to cheat on exams when the teacher's not in the room watching you. I'm not going to make you put a camera on you, and all that sort of hoopla. If you cheat, you're cheating yourself, and you might get caught. If you get caught, I will get you called up on charges at the school, and you'll probably get dismissed from the school, and it will follow you forever. So you don't want to cheat. When I give you suggestions of how you should take an exam, you want to follow my directions exactly. Do it on your own. If you don't do well, I'd rather you not do well without cheating than to not do well by cheating. And so, or even do well by cheating. I mean, that means nothing to me. So you want to make the goal, one of your goals, to be that Bostaine realizes I'm good at this, and he'll give me a recommendation someday when I'm really needing it, because he knows that I'm an honest person and I really gave it the good old try. So yes, I know you could cheat on those and get 50% for almost nothing. Don't. And the other half is labs, participation, and homework. There are a few homework assignments, particularly when we get into the programming section. There'll be some labs, particularly toward the end of the semester, where we actually have to apply some of the things we know to writing some programs, perhaps in class, that will be used with our ATmega 328P chip. Finally, the last and really important one is participation. Now, participation means that you're here all the time in class. You got here at 6, you left at 8:20 when I stopped class, and that any time I ask you to hit one of those buttons at the bottom, you hit the button. I keep track of every time that I ask for that and who hit the button. If you don't hit the button, I'm assuming you're away from your desk, which means you're not fully participating. So everybody right now, hit the button. Hit the one that turns it green.
Sorry, I was late. What button is that?
You have to get that from another student on a different day. Okay, so now I see Oscar. Peter did not. Okay. I think we had a dolphin in the class. Okay, so most of the people found it. Okay, now they'll die away after a little bit of time. So anytime I ask you to do that, one of the things you're going to need to do is hit that button. And part of your participation grade is going to come from your attendance. It's going to come from the ability to actually participate when we have an exercise. I may give you some little mini, won't call them quizzes because they're the sort of thing we immediately go over the answer, so there's not really like a mini test. It's more of a opinion poll type of a thing. And participation in those means a lot. Okay, notice down at the bottom there's a little subtle hint that participation, attendance, and punctuality are expected, okay? Not just they're optional. They need to be definitely done. Okay, next page. The approximate schedule for the course is listed here. I'm not going to go over every item right now, but what we're going to see is the class is kind of divided into 3 major components. The first component, which starts with Unit 1 and runs down through, well, actually through here, is called combinational logic and Boolean algebra. This is basically logic type statements which will allow us to, in immediate time, see the results of some inputs on an output. Now, we really know in the real world that can never happen. We know that the speed of light is just slightly faster than electrons, right? So that becomes a limit for us, but the electrons themselves take some amount of time to go a distance. So if we have a chip or a board where there's a distance between where a signal enters the board and where it needs to exit again, we're going to have a finite amount of time that actually has to take place before the logic can switch. However, we're going to study the logic, first of all, assuming that that delay does not occur. That's going to help us be able to understand the principles without getting into the nuance of the implementation. We will get to that. Don't worry, that will happen. The second section is called sequential logic, and it begins about here and makes it down through, I would say, yeah, but let's include VHDL in that as well. So this is pretty much sequential logic. Sequential logic has to do with logic which is presented to us in some sort of order, where the order matters. For example, when we design a central processing unit in the third section of the course, one of the things we're going to see is that it's necessary for us to build these little mini programs which describe what an instruction does. And those little mini programs that we have defined are actually sequential logic. This has to follow this, this has to follow this, this has to follow this. And they themselves take care of taking combinational logic and using those sort of, that algebra to determine what the processor should do next. So we'll learn quite a bit in here. In particular, a very interesting section is a section on what we call finite state machines or finite automatons. And you'll find out that an awful lot of computer science is based on understanding those. At the end of that, we will have our first exam. The first exam will cover all of the material up to that point and is pretty much inclusive back to day one. So some of the things I told you at the start of class, those will be on that exam. So you need to make sure that you're taking good notes throughout. Now, don't write down everything I say. That would be just dumb. What you need to write down are the things that are important that I'm saying. How do you figure that out? Well, you need to listen to what I'm saying. If I tell you what I had for lunch, that's probably not important. If I show you an example of how something works, you want to jot down if you understand how you would apply that particular thing. Then later, you want to take those notes and rewrite them. If you have everything we talked about on the piece of paper and you go into that exam, you'll never find what you need in time to answer the questions. So you need to make sure as you go along, you understand what we're doing as we go, and that you synthesize what we're doing into something that means something to you. It may not mean anything to anybody else, but your notes are for you to use. After the first exam, we're going to explore some microprocessor and processor architectures. We're going to do the SAP 1, 2, and 3, then suddenly realize that the SAP 3 is really an Intel 8085 processor minus a couple features, which will give us a way to talk about some real-world processors after we've designed the instruction sets for these. And we'll see that what we designed worked out to be this instruction set. Then we'll talk about the 8088 architecture. The 8088 is the processor underlying the desktop or laptop that you're using now, more than likely. And Pentium chips, all of the i7s, 3s, 5s, all that sort of stuff, all are rooted in the 8088 architecture. We will learn its instruction set, which to this day is still valid and works on all those processors. It's not complete because they've added new features, but it'll be sufficient for us to really take a look at a machine which happens to be of the type complex instruction set and also happens to be a Princeton or von Neumann architecture machine. We will have a second exam which basically emphasizes these, but by necessity goes back and includes all of this stuff. You can't do the second section without knowing this, so by necessity, we have to use all of those steps here. This isn't incremental and you do something. Well, it is incremental. It's not unique that you do something and then can forget about it. When I tell you you need to learn your powers of 2 up to a certain number of powers, you're going to be using that the last night of class, even though I may tell you tonight to do it. So you want to make sure that you have spent a little quality time doing the homework and make sure that you don't just put them back burner things we did back here because you don't expect to see it again. This class tends to be a whole lot of disconnected things that all start falling into place somewhere near midterm. Then we'll have several lectures. I'm not sure if it'll be 4 or 5 or 6, but we'll have several lectures on the ATmega 328P, and it happens to be a reduced instruction set computer that uses the Harvard architecture. So we had the complex with Princeton architecture, and we'll have the reduced instruction with the Harvard architecture to really dig in and learn how to program these using assembly language. Finally, if we have time, we'll have a review unit. If not, we'll have done enough review through most of this that you won't need it anyway. And then we have the final exam. I don't pick when the final exam is, the school does, so we'll have to wait until they publish a date for it. They may have done that already, I just haven't looked it up. So those are the things you can expect to see over the next sessions. Notice initially tonight, we're going to talk about some number systems. We're going to talk about encoding characters in ASCII. We're going to look at the Unicode standard, which kind of is the new way of doing ASCII. And then if we have some time, we'll talk a little bit about Ohm's law, some resistors, and some starting circuit stuff. Although we probably won't do a lot of that tonight. Although over the next couple of classes, we minimally will get up through transistor circuits. And we need to know those because when we talk about transistor logic down here, and later we talk about some other architecture things, for example, tri-state logic, we need to be able to see how those would be built and understand them in terms of their transistor contents. If we were meeting face to face, we'd be actually building these. I would give you the parts, we'd sit down, have lab time, and we'd actually build these. Since we're not, we'll have to do it through simulation. But it'll still be very meaningful, and you'll find it to be a useful thing to have. Think how cool you'll be being able to go to a party and, you know, when everybody else has nothing to say, you can talk about bipolar transistors. Be so cool. Okay, so we're going to start when we get talking here about number systems. But before we do, and again, I remind you down here, the participation, attendance, and punctuality are expected. Does anybody have any questions about any of the things we have been talking about so far? If you do, one at a time, you can turn your microphone on and you can ask the question. It's okay if you don't.
Just a small question, Professor. You said we needed a grocery store calculator.
Yeah, I would get something cheap. If you got a big TI-88 or an 89 or something that you just hit one button and it, you know, does ASCII to Unicode conversions, you won't learn how to do it. And then when you do it on the test, you won't have the calculator and you'll not be able to do it. So something cheap. Mine cost me exactly $1. And it was sitting there right next to the little eyeglass screwdrivers, you know, at checkout, somewhere near the Dove bars or something. Something was sitting there. I got one of each. And they all cost me $1. And probably cheaper
I
to
have
go.
a scientific calculator right next to me. Does that work, or should I get something even more basic?
As long as you don't use any of the features, you could use the fanciest computer or calculator in the world. But don't get tempted into doing base conversions on it or something like that. I find it myself.
I know how to do it on this calculator.
Okay. Okay. So, anybody else have a question? That was Nicholas, right? Yeah, Robert. You'll need the board by at least midterm. Okay, you got your speaker on. Make sure you use headsets or something if you're going to use your microphone because it picks up and feeds back really badly. Anybody else have a question? Okay, I recognize a lot of the names on here, and I know some of you guys are really smart, so I'm looking forward to that. I hope the rest of you can keep up with them. Some of them I had in the spring in a different class, and a couple of them did especially well. So hopefully they will continue doing that in this class. The other thing is, if you got into this and it all of a sudden seems like you shouldn't be here, get out before I have to fail you type of thing, because if you really do terribly, somewhere along the way, if you don't come to class, I have to withdraw you, and I have to withdraw you qualified with a failing or passing. So if you're going to not come to class, drop out, because it would be the only sensible. And I don't want anybody to. Everybody's capable of doing this if you spend the time and you know, make friends with other people in the class, or at least have contacts so you can do the work. But for some people, this just isn't the place they should be. And I'm not trying to discourage anybody by saying that. I'm not sure anybody fits that bill right now. But I've had it in the past happen. Okay, so I need to make one adjustment here, and then we'll start talking about number systems. And it looks like on the clock on the wall there, I'm right on time. So let me do that. Okay. If you can hear me, hit your green button. Okay, so I'm going to be in base 10 for a second. That's what we're used to using. I'm going to write down the number. Well, that's fine. 1242. Whatever comes out of my keyboard here. My keyboard, unfortunately, does not have keycaps on it, so I have to guess where the keys are. And to be honest with you, I had typing when I was in 9th grade, and I was probably in 9th grade in the early 60s. So you can imagine that I don't have memorized where all the special characters are on the keypad. So if I mistype something, I'll try to go back and fix it because I have a general idea, but don't expect me to type perfectly. So what does this number really mean? It means I'm going to take 1 times 1,000 and add it to 2 times 100, add it to 3 times 10, or 4 times 10, and then add a 2 times 1 to that. So we know positionally what each of the positions stand for. If you're in the 4th position to the left, you're in the thousands column. The hundreds is next, the 10 is next, and the 1 is next. If we think of these in terms of powers of 10, we'll find out that's 10 raised to the 3rd. That's 10 squared. That's 10 first. It's 10 raised to the 0. So as we move across, we see that the power we raise the number to is the base we're operating in times its 0-based position. So if I were to write those numbers underneath here, we see that each position actually has a power of 10 we need to raise that position to in order to determine what the final answer is. And all we do is we raise that number and then we add it to all the other positions. So each position has its own value and each is scaled by some power of 10. Now this would be true if I operated in some other base. Let's say I wanted to operate in base 8. I could write down the number 135 and say I'm in base 8. Well, what does that really mean? We know that this is going to be 8 squared. This is going to be 8 to the 1st, and this is going to be 8 to the 0 power. So we'd have 1 times whatever 8 squared is. Well, 8 squared is 64, and this is a decimal number I just typed. Plus 3 times 8 plus 5 times 1. So if we add those up, we get 64 plus 8, which is 72, plus 1, which is 73. So what we really did here, and I'm writing in base 10 or decimal right now, we took 8 and we raised it to square. We took 8, took it to the 1st, took 8, and we raised it to the 0 power. Remember, anything raised to the 0 power is 1, so that guy is going to be an easy one all the time. So if we saw the number 135 and somebody said that's in base 8, normally we'd stick a little subscript after it that said it's in base 8. So subscript, by the way, would always be in decimal. So even though this number was in base 8, if I were to stick, I'm going to pretend like this is a subscript. If I were to stick an 8 down here, you'd have to know that that was in decimal. Otherwise, you'd be confused. I can't write it in base 8 because if I write it in base 8, it's going to be that. How would we know that that's base 8, base 10, base 16, base 35? We don't know. So we have to agree that any subscript is going to be in decimal to indicate the base number. I can't do that with this editor, so we'll just have to forget about it. So this is how you would go about creating a number and realizing position. So if I'm going to do something in binary, which is where we're going to spend a lot of our time, we're going to just simply take the positions and we're going to assign them values. So let's see. It'll be 6, 5, 4, 3, 2, 1, 0. That would be the power of 2 that we have to raise in order to get that value, and then we'd sum up what we have. Now, interestingly for this, that means what we're really going to do is take 1 in binary times 2 raised to the 6th. 0 times 2 raised to the 5th. 0 times 2 raised to the 4th. 1 times 2 raised to the third, 0 times 2 squared, 1 times 2 to the first, and 0 times 2 raised to the 0. So we can actually compute what those values are. We'll do it from the bottom up since I'm down here at the bottom. So we have 1, 2, 4, 8, 16, 32, 64. We know what number we have. We could take 1 times decimal 64 plus 1 times decimal 8 plus 1 times 2, and we get the number 74, right? It'd be 64 plus 8 plus 2. Now, what's especially convenient in binary is the fact that these numbers are always either 1 or 0. 0 means ignore me, don't even bother. So all I ever have to keep track of would be the ones that have a 1 next to them. So I can take and I can compute a number. If I were to know my powers of 2 in a binary number and convert it to decimal very, very easily by simply looking at which one of the bits, and a binary number that is used the digit 0 or 1 is called a bit. It stands for binary digit. And we can kind of think of this as being the alphabet. These powers of 2 is kind of being the alphabet that we work with when we're working in computer science. Now, by alphabet, I mean, like if you were in, very early school, they taught you your alphabet because when you're today writing down things, you don't even want to think about the alphabet. You don't even want to think about words, probably not even sentences. You want to put together paragraphs of thought. Sentences maybe, but words, you just kind of pick a word here and there along the way, but you don't want to have to re-understand the concept of a word or look at something and determine whether it is a word or not. That sounds too much like Scrabble to me. And the other thing is, you need to be able to think of these things and do them readily. If somebody were to write down a number, just kind of at random, and say, what is that in decimal? Well, you should immediately say it's an 8 plus 2 plus 1. And if you do that, you see that's an 11. So writing them down, you should be very simple to do. If I wrote down this number right here, you should say, well, that's a 16. Because it's 2 times, or it's 1 times 2 raised to the 4th. So we'd be able to determine that, this number right here, where did they go, is actually the decimal number 11. And this number right here is the decimal number 16. But we need to be able to think about binary. Now, binary, as I said, is good. It's great for electrical systems. It's great for anything that has to do something that informs logic, because we can make the 0 stand for false. We can make the 1 stand for true. Or we could make it be a 0 and a 1, or a yes and a no, or anything that's dichotomous, anything that you can break into a dichotomy. It's either this or that. We could represent with a binary system. And binary itself is very straightforward. The positions have very specific names and values. One of the things, and this is one of your first homework assignments, so you want to write this down because by Monday you need to have this done, is you want to learn and memorize all the powers of 2 from 2 to the 0 up to 2 raised to the 16th power. And when you do that, what you want to do is you want to be able to go both directions with them. So let me, again, I'll post this table for us. You need to learn from 0 to 16 here. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16, 384, and 32, 768. I'm sorry, 32, 760. Well, so I missed one here, 65, 536. I had it highlighted. These values are important to know. And if I give you one, for example, if I say 2048, you should immediately know that's 2 to the 11th. If I give you the number 64, you should immediately know that's 2 to the 6th. I will use these as a measure of how hard you're trying in this class. From this point forward, anywhere I see you, I might, in the middle of your wedding, when they say, does anybody object? I might stand up and wherever you are and say, I don't object if he can tell me or she can tell me what 2 to the 11th is. So be waiting for it. I had a student one day. I had some mail misdelivered to my house, and I noticed the address when it was close enough. I just took the mail to their house, and while I was there, this guy came up, and I noticed I recognized him. It was one of my students, ex-students. I immediately asked him what 2 to the 13th was, and he immediately responded with 8192. This kid got an A, even got an A in life, because this was long after I'd had him as a student, several years. So you don't be the guy that doesn't learn this stuff. Now, another thing you might want to keep in mind is you should also kind of know what one less than these values are. It's very common to be asked a question like, how many values will fit in 8 bits? Well, 8 bits will contain 256 values, but the values they contain start with 0. So there will be 0 through 1 less than that. So 0 through 255. So knowing what 1 less than the power of 2 is a useful thing to know as well. Sometimes here, 65,535 is a very common value because it's in hexadecimal, it's FFFF. And so sometimes that's a number where it's going to be very common to have to know what the value is. 32,767 is a very common number you'll see. 16,383, the common value you'll see. 255 is another one. So memorize these. They're not hard. I know it sounds like it's an awful thing to do. Be glad I didn't go any further. You know, way down here at the bottom, well, 2 to the 256 is this number here. It runs off the screen. There it is. Many, many years ago, I had a student. He was 13 years old. His name was Ettrick Patricelli. I challenged him to a free Big Mac or a free Whopper, I forget which it was, if he could memorize that number. He did it. Don't know how, but he did it. But he was also in college at 13, so he had a couple other things going for him. So we're not going to have to memorize the whole chart. I will post it out there for you so you can enjoy it and you can share it with your friends. So that's your first homework assignment. Write that down somewhere because you're going to need to know that. Now, the next kind of thing we wanted to talk about was, remember we said these are called bits. I'll just lowercase it, bits. And a bit it's called that because it's a binary digit. And so what they really did, right, is they got rid of the nary and they got rid of the dig, and what you got left, well, I got rid of one of the i's too. They got a bit. So a bit is either a 0 or a 1, can stand for a true or a false, and is, quite meaningful. Oh, hang on here a second. I think I'm going to sneeze. We'll see if I can get. Didn't make it. Had to sneeze. I have a cat, and the cat is walking back and forth across the table right now. She knows there's some treats in the other room, and she figures that I'm going to go get them for her. Well, I can't right now. I got you guys, so she'll just have to wait. But she ran her tail right under my nose, and it made me sneeze. That's Miss Lucy, by the way, in case anybody ever asks you. Miss Lucy the cat. Okay, so if I were to say I'm going to give you my phone number, and I'm going to give it to you in binary. 101110111011101111, and that's just the area code. Not quite as convenient to communicate in that as it is base 10, because if I told you my area code was 908, you just remember that. You can remember up to about 7 things pretty well. But when you go beyond that, then it's a little more problematic. So what we have is the idea of let's group some bits together. What if we were to take them in sets of 4? Like that. And then remember what these values are. Well, I can compute them, right? In this case, the 8-bit is on, the 4-bit is on, the 1-bit is on. So that's 12 plus 1, that's the number 13. If I heard 1101 and in my head I remembered 13, it would be a little easier. This one obviously has no bits on, so it's going to be equal to 0. This has all the bits on, so it's going to be equal to 15. I'm going to show you a little trick here. You remember 16 look like this? The number that's 1 less than a particular number that has, a unique bit. So any number you can represent as a power of 2. The number that's 1 less is always throw that bit away and just keep the other bits as all 1s. So if I gave you a number that looked like this, and I said, what's 1 less than that? We could simply take the same number, get rid of the first 0 that's there, or first 1 that's there, and then turn all the rest of them into 1s. Now, chances of me typing those all without counting them is poor. So it's 1, 2, 3. We got 8, 9, 10, 11. So it would be 11 1s. And that number turns out to be 1 less than that number. And it's always that way, no matter what power 2 you're talking about. And that's a good thing to remember. And I'll show you why later. But if we were to take all of the numbers in 4-bit groups, one of the things we know is that if each position could contain one of 2 things, and we have 4 positions, that means that we have 2 raised to the 4th number of combinations of those that we could get. So let's write them down. Okay. So I have written them down. Now we could go through and we could figure out what each one is, unless I systematically somehow wrote them down. And I, in fact, did systematically write them down, such that they're going to go up by 1 number between each. So this is the number 0, number 1. 2-bit is on, so it's the 2. In this case, the 2 and the 1 are both on, so it's a 3. In this case, the 4-bit is on, 5-bit, 6. So 6 is 4 plus 2. 7 is 4 plus 2 plus 1. 8's the power of 2. 8 plus 1 is 9. 8 plus 2 is 10. 8 plus 3 is 11. 8 plus 4 is 12. 8 plus 4 plus 1 is 13. 8 plus 4 plus 2 is 14. And 8 plus 4 plus 2 plus 1 is 15. So this binary number is equal to that number in decimal. So if somebody said to you, what's the number 7? You just would know it's 0, 1, 1, 1. Now, conveniently, if you think about it, we have 15 digits. Well, say actually, if we have 16 because we count 0. In a particular base like 10, there is no number that represents 10. In base 2, there is no number that represents 2. You always go 1 less than the base. So it seems to me that each of these could also be represented by a base 16 number. So let's write down some numbers here. We know that the first set are going to be identical to their decimal equivalents. When we get to 10, we're in trouble. We need a single digit which can take only one column, but we've run out of all our digits. That's a problem. And so we're going to have to deal with that. And in order to make that happen, what we're going to have to do is we're going to have to invent some characters. Now I could write some sort of squiggly something there and make up some new characters, or I could just simply, let's use the alphabet, either upper or lowercase. Okay, if we're talking to somebody, we'll give them names. A needs to be some sort of sounds like thing, so we'll call it alpha. Bravo or beta, Charlie. Delta or dog. Easy or echo, something that's going to make it stand out from all the other numbers. Foxtrot or fox, depending on whether you're a pilot or not. So the numbers in base 16 are 0 through F, or 0 through fox. We also now have a single-digit solution to this 4-bit pattern item. So if somebody says, I have a pattern of 1011, what is it in hex? If you had that memorized, you just know it's a B. You'd also know that B is really decimal 11. Now this is convenient because now we can write long strings of binary numbers using hexadecimal. And that turns out to be rather convenient for us because if we had, for example, the word cafe, which is all in binary or in hexadecimal, right? C, A, F, E. Now, that doesn't spell cafe in something you could print out. That's really rather the 8 bits C and A, the 8 bits F and E. Just happens to be the word cafe when we spell it out. We could equally do the same thing with some numbers. Say we had the numbers 32 dog alpha. 3, 2, dog, alpha. Wrong key there. So the 2 and the 1 bit are on, the 2 bit is on. 8, 4, and 1 equal 13. We look at 13. 13 is a D. 8 and 2 are on. That's an A or alpha. So that's going to be a 1011 or 1010, which is the A. So we can make any hexadecimal value. We can collapse these sets of 4 digits into a single hexadecimal value. And sometimes we'll do that. Now, which base are we usually using? Well, we have to know which one it is in order to communicate. But in this class, generally, it's going to be something in hex or binary unless it's obviously in decimal. And you're just going to have to kind of figure it out. And you won't have much trouble because context will almost always give it away. Now, one of the things we can also do is we can take a number like 100 and we can turn it into binary. That 100 is in decimal right now. Let me write decimal next to it. The way we're going to do this is we're going to take the largest power of 2 that's smaller or equal to the number, and we're going to subtract it away from our number. We look over here, looks like 64 is the first number we can subtract away. So minus 64. That leaves us with 36. What's the biggest number that's equal or less than 36? What's a 32? That leaves us with a 4. What's the biggest number less or equal to? Well, 4 itself is equal to that. So we can subtract 4. That gives us a 0 or the final sum. Once we hit 0, we now know which bits to turn on in order to represent that number. So let's write it out as though it were a byte. 1, 2, 3, 4, 5, 6, 7, 8 bits. This is 2 to the 7th, the 6th, the 5th, the 4th, 3rd squared, 1st, and 0. So 2 to the 64th is 2 to the 6th. So we know the 7th is not on, but the 6th is. We know 32 is on. That's 2 to the 5th. That's why we have to memorize that table. I got it showing right now, so you haven't memorized it yet, but you need to know it. 16 is not in there anywhere. 8 is not in there. 4 is. 2 is not. 1 is not. So now we have 0, 1, 1, 0, 0, 1, 0, 0 in binary is equal to the number 100 in decimal. We also could write this as 6, 4. We don't say 64, we say 6, 4 when we're in hexadecimal. I just took this and said, well, that's a 6 from our table up here, remember? And then I took this and said, that's a 4. We didn't have to, because I could have just looked at that and said, well, the 4-bit and the 2-bit are turned on, and here the 4-bit is on. So I could compute that that has to be a 6-4. I also know that if this is in base 16, the 4 is times 1, and the 6 is times 16. 6 times 16 is 96, plus 4 equals 100. So that's a quick way to do a conversion from, decimal into binary and hexadecimal, or any other way using one of these techniques we've been using so far. Okay. I'm going to move on to the next topic, and give me a green light right now if you're reasonably okay with what we're talking about. Yeah, I thought you would be. Okay, the next thing we have to think about is if somebody were to give us a number in binary like this, and they said they wanted us to be able to augment that number to become 129. Well, right now it's the number 128. We know that all we'd have to do is add a 1. But what if somebody came to us and said they wanted to do 126? Well, this is 128, right? Well, if that's 128, how could we get 127 easily? Well, we could take this. Remember, if you took and made it a 0 and then everything to the right turned into a 1? And then we could simply say, well, if that's 127 and I want 126, all I have to do is get rid of 1. And then I'd be able to do a number which is close to a power of 2, almost in my head. Obviously, if I have a pencil and a piece of paper, it's a piece of cake to do. Okay, new topic. I'm just going to say ASCII Wikipedia. Not spelling it that way, I'm not. Okay, ASCII is a code which is used to encode in 8 bits, really 7 bits, all of the common things that you would print or that you would get off of a keyboard prior to the United States discovering the rest of the world. But it is very pervasive all the way even on the web up through HTML4. And in many programming languages, ASCII turned out to be the code of choice. Now, we can't just send numbers in their pure binary form. For example, if we wanted to send the number 0 over a wire to another location, and we send it as a byte, it would be all those zeros. It turns out that most communication channels need bits to change frequently in order for them to stay reliably clocked. And that would not be a good way to send a 0. So what we do instead is we encode them in ASCII, US ASCII in particular. ASCII stands for, and I always have to look it up, the American Standard Code for Information Interchange. And for a long time, literally was the code that's used, and we still have to know it and support it because it's used in microcontrollers quite a bit when we're communicating among chips and boards, not so much among humans any longer. What we're going to do is we're going to find that we need to encode some very particular things. One thing is we need to be able to encode the numbers 0 to 9 so we can print them or receive them. We also need to be able to encode the numbers A to Z and A to Z, the 8 letters. Another thing we need is we need a space character. We also probably need a carriage return and a line feed or something so we can get the new lines. And the uses of them vary depending on your operating system, so we just have to know them both. So what I want to do is I want to grab a copy of an easy-to-read ASCII chart. Hopefully I spelled it right. And I'll post this for us. We're going to look at where those things live in the chart. First of all, let's find the numbers. They're right here, 0 to 9. In hexadecimal, they all start with a 3. 30, 31, 32, 33, 34, 35, 36, 37, 38, and 39. So in order to take a number and turn it into its ASCII equivalent, you simply add the number 30 in hexadecimal to the number you want. So this is 30 plus 1 is 31. We want the number 6, it's 30 plus 6, or 36. So all you have to memorize, and again, this is an assignment. We have 2 assignments so far. One is to learn your powers of 2 from 2 to the 0 out to 2 to the 16th. The next one was to learn the hex to nibble conversion. I didn't mention that. Let me mention that while I'm looking at it on the page here. These things taken 4 at a time like this, and this is the table you need to memorize, all 3 columns. When you take 4 bits together or you have a single hex digit, it's called a nibble. Nibble being a small byte, right? Smaller than a byte, which is 8 bits. This is 4 bits. You might see this spelled, which is actually incorrect, but recently has become more accepted. It simply means 4 binary digits or a single hex digit. It's called a nibble, and it's half a byte. Meanwhile, back over here, we have 2 nibbles. So the 3 stays alone. If you remember 30, you can compute any number by simply taking the number and adding it to 30. To learn the uppercase letters, you simply take the position of the letter in the alphabet and add it to hex 40. So if it's the letter J, for example, which is a 10th letter, we simply add the number 10 to 4. So 4 plus 10, 4A. A is the hex digit for 10. Notice by the time we get to letter P, which is the number 16, we've overflowed that column and it's going to have a 5 in front of it. But we still simply took 40 and added 10 to it. 10 is 16 in hexadecimal, which would give us 50. And the highest we have to go, obviously, is 26, higher than 40. So if you remember 40, you know how to compute where all the uppercase characters are. Same thing is true for the lowercase, except they're relative to 60. Space is at 20, 20. And then the only oddball ones you have to remember are carriage return is at 0D and line feed is at 0A. Later on, we'll probably want to learn something like horizontal tab, but we'll get those on a separate time. So you'll need to know, that's your 3rd piece of your homework, right? Memorize where in the ASCII table numbers are, letters are, upper and lowercase, where space is, and where the carriage return and the line feed live. So if you want a quiz, or not a quiz, a mini exercise, we're given a problem of take the ASCII character for BAD3 and encode that in ASCII. We know B is the 2nd letter of the alphabet. It's capital letter, so it's relative to 40. So it'd be 42. A is relative to 6 because it's lowercase. It would be 6, 1. D is the 4th letter of the alphabet. It's lowercase. It would be 6, 4. 3 is a number. It's relative to 30, so 3, 3. That's the ASCII value of BAD3. Normally, we would write each character separate like that so we could indicate that they were letters of a word. So I will post this, but this is the third thing. I think it probably is the main other thing in your homework, because I don't remember a lot of other things for you to have to do other than memorization for this exercise today. Okay, so this is the ASCII chart. Problems with the ASCII chart. Number one, machines love it just fine because they've got all these control characters and things they can send back and forth. And plus, it's only 7 bits. So when we did discover things like France or Germany or Russia or other countries, one of the problems we had was we don't have characters they have in this character set. So if they have a character with an umlaut over it or something, or an accent, we don't have a character which can represent that. We don't have, some of the characters that are in German, certainly not the alphabet that's in Russian. So what was originally done, the other values, because there's 128 characters here, the other 128 inside of the first 8-bit byte, which would make it 256 characters, were given to individual countries. And you had to know which country you were working with in order to know how to encode things in the second half of the ASCII chart. That was done for years, and I mean decades worth of years. But then finally we realized there's a lot of business to be had in the rest of the world, and our websites are a little hard for some people to read. Although English is pretty well spoken throughout the world, it isn't as universal as we think, and also it's pretty hooty on our part to be able to tell people to have to speak English to do business with us. So what happened is we needed a better code, or a more flexible code. The code that replaced what we're looking at here, the ASCII chart, for people-to-people type communication, and turns out to be the code of the web, is something called Unicode. And Unicode has a very large standard and a large following, and it's probably going to be the code we use for many years onward. Let me take us to a page for that. Okay, Unicode, here's the idea behind it. We're going to use more bits. In ASCII, we only had 7 bits to use, and we had 8 if we wanted to internationalize it, which only gave us twice as many characters. But somebody went out one day and they looked at all the countries that we've been creating characters for, and they said, we probably will never need more than 65,536 characters. 65K or 64K worth of characters. And so let's extend the basic unit for characters up to 16 bits. And the developers of languages like Java and C# and things like that got on board really quickly to that. Here's the Java development video. What do they say? Yay. Okay, they really like Unicode. So what they did is they wrote Java to support 16-bit Unicode. So did C#. I'm picking on Java because it's one of my friends. And you may not know this about Java, but other than the keywords, almost everything else in Java can be written in any language you choose in their character set. So if you want to write it in Egyptian hieroglyphs, you can, as long as you keep the keywords in English. And of course, the numbers they follow the pattern of being English numbers. But the rest of the words, like variable names and things like that, you could have a variable named King Tut if you want to, and you could use his hieroglyph for that. But a problem Java ran into was even the Unicode people early on suddenly realized they didn't allow enough space for all the languages of the world. They kind of forgot initially about languages that were Asian, because there were very, very many characters in a lot of the character sets there, and lots of variant character sets. Then they found the Native American languages that needed to be stuffed in there. And then they found a bunch of just traditional languages that people had forgotten about. And today, Unicode has 21 bits worth of data. The biggest number you can write in Unicode today is that, biggest character value. Well, bad news to Java. You only got 16 bits to stuff a 21-bit number in. Java development team, Oops. Well, that didn't forego them. The actual code they use is something called UTF-16. Unicode codes generally start with the letters UTF. And there's variants of these that we would see. And let's talk about those for a second. UTF-16 comes in two flavors. One is called Big Indian, the other is called Little Indian. Indian is spelled E-N-D-I-A-N. It doesn't have anything to do with Native Americans or people from India or all the other names that people use India for. Indian, in this sense, has to do with Gulliver's Travels, the story, in which there are a place he visits where some people like to stand their eggs on the big end and some like to set them on the little end and balance them that way. And because really what we're talking about with Big and Little Indian character sets has to do with processors, there's two main types of ordering on a processor memory. Either you go from high bit to low bit, or you go from low bit to high bit. If you go from high to low, it's called Big Indian. If you go from low to high, it's called Little Indian. And so since there are processors out there of both types, we need to be able to specify codes which can extend from the UTF-16 standard, but nevertheless fit into both. So if I had a 16-bit code like that in Big Indian, and I wanted to rewrite it in Little Indian, I would simply take the second byte and put it first. So this is Big Indian, this is Little Indian. If I have it in Little Indian, I just reverse that. And I do it on a byte basis. Although I write it out since it's 16 bits as a foursome, a nibble, or part of a nibble. Well, yeah, a different type of nibble. So I'm take that word back for the moment. It's 16 bits. Since I'm using 16 bits as a whole, I'm going to keep all 16 bits together. Each of these individual things are nibbles. Two of them taken together are a byte. And since it's bytes I'm reversing, that's why I get the artifacts that I'm having here. Now, there's a couple of ways that I can do UTF-32. I'll show you a somewhat standard way, but there's a second way, and I'm not going to bother showing you. Let's assume for a second that I had a number which filled 32 bits. In Little Indian, I would just simply take and reverse the bytes. Because 32 bits is so much larger than 21, it can definitely contain all of the codes. But there's a lot of wasted bits. So it turns out UTF-32 and its other variants of UTF-32 aren't used as much as you might think they are, particularly on smaller machines or on things that need networking, like the web. They just don't tend to work out as nicely. Now, there's one other encoding which does not have Big Indian and Little Indian notations, and it's a code called UTF-8. UTF-8 uses a form of compression, and we'll see what that means when we talk about it in a couple of minutes, because we need to be able to code things into each of these standard encodings. And I'm going to give you kind of some simple ways to do it, but then you also have the whole website that's dedicated around Unicode. And you also can go and start looking from the Wikipedia outward about some of the words and terms you're going to hear. So if somebody asked me to encode this number right here in 32-bit Big Indian, let's just kind of do that. So the number the biggest number we'd encode would be this. We'd need to prefix it with some zeros. And we want to make sure we have 8 of them. I think we got one too many there. 1, 2, 3, 4, 5, 6. We still got one too many. So we need 8 bits, 8 hex digits, 16 hex digits here. Or it's 8 hex digits. I'm not counting right. So this number would fit just perfectly into the thing. And if this is the Big Indian form of it, we could flip it around the other way. Now, you'll see other ways of doing the flip, but for our purposes right now, we'll assume that we took that ordering for little endian in UTF-32. So that number was not too hard to encode. Let's take the number 1023 and encode this number in UTF-16 big endian. How would I do that? Well, because it's already less than 16 bits or 16 bits or less, I just encode it. If it had been UTF-16 little endian, I'd do the same thing, except when I got done, I'd reverse the bytes. So there's no problems yet. The 32 is easy. UTF-16, as long as it fits in 4 nibbles, it's easy to do, and it's not that much harder to do the little endian flavor of it. But we do have a problem when we get to our big number here, 10FFFF. And the problem here is it doesn't fit in 16 bits. So we're going to have to use something called surrogate pair. Now here's how a surrogate pair works. We're going to take a number that does not have a character associated with it, which is D800. And as a matter of fact, all the characters up to DFFF do not have other characters associated with them. So we're basically going to take D800, and we're going to take D Charlie 00, which is about halfway, and we're going to call those part of the surrogate pair. One is called the high surrogate, the other is called the low surrogate, and they introduce the surrogate. Since I can never find that combination anywhere else, I can never confuse this for a 16-bit number. Then we're going to attach to this number pieces of this number after it's been split into its 2 components. We have 21 bits, so that doesn't divide evenly. So we have a little exercise to do first. First thing we do, we're going to take our number and we're going to subtract from it that value right there. It's always that value. So obviously we couldn't take that number from anything that was 16 values because we would be creating some sort of a negative value. So we just look at these numbers here and pretend like we know how to do arithmetic. We have the number 16 minus 1. Well, 16 minus 1 is 15, right? So if I replace that number now with this, I've got the result of that subtraction. So that number now needs to be split into 2 parts, which are each 10 bits long. And we know that because how many bits we have? We have 1, 2, 3, 4, 5 nibbles. 5 times 4 is 20. We split that in the middle. We're going to have 10 bits in each half. So I'm going to write it in binary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here's the other half. And then 1, 2, 3, 4, 1, 2, 3, 4. So I took the center nibble and split it into 2 halves. Now I have 10 bits here, and I have 10 bits here. Now what I need to do with this number is I need to add this and this to their corresponding surrogate portions. So this number right here needs to be added to D800. This number right here needs to be added to D Charlie 00. So let's kind of do that. First thing I want to do and I'll leave this printed like this, so if you're copying the notes as we're going along here, you'll understand the steps later when you see them. First of all, I'm going to collapse this so that the 10 bits are all smushed together. Then I'm going to come back and I'm going to make it so that the 2 bits that we have separate are leading. Now this one didn't have to be squished, but just shows what happens. Okay, now this is 10 bits. We're going to be adding it to a 16-bit number. That means I need to have 6 zeros in front of this. 2 of them will go with that. And then we need to have 4, I'm sorry, I need 4 more zeros. So we have 6 zeros in front of it. Same thing here. So now this number is able to be added to D800, and this number is able to be added to D Charlie 00. So let me write those numbers underneath each. I'm going to actually break this down to its own line just to make it easier to see later. So let's say we're going to add this to D800. And the other guy we're going to add to D Charlie 00. Now the addition here is trivial because everywhere that we have a 1, there is a 0 beneath or above it. We never have 2 ones lined up together. So the addition here is going to be rather simple. It's going to be 1101, 1011, 1111, 1111. And the other guy, we add him up, 1101, 1111, 1111, 1111. Now let's rewrite them back out in nibbles again, in hex. So the first guy is going to be DBFF. The next guy is going to be DFFF. So the answer to our problem is DBFF, DFFF. This is this number in UTF 16 big endian. Now, if it were a little endian, because we're working in 16-bit entities, it would be FFDB, FFDF. So that's the little endian form of the same thing. Okay, now give me a mildly confused button if you're mildly confused. Give me green if you're totally happy and understood all of that. Yeah, I thought some of you would. Yeah, some are confused a little. That's okay. Okay. Now, if we notice one thing here, we use the biggest Unicode number there is. We also got a value that was added to this guy, which was DBFF. From this guy, we got a value which was DFFF. If you notice, that makes sense because that range is below this. This is the very next number after that. It would make sense that the biggest number would use the biggest first value. It also used the biggest second value because if we go any higher than this, we're going to go to E0, which is no longer identified by one of these surrogate pairs. So a surrogate pair is something you need to be able to do the conversions on. Just remember, it's little endian things that happen are always done in 16-bit entities, even though the number itself is a 32-bit number now. This has 4 bytes in it. Okay, let's do another one of those. I think doing one of those as just a practice item would come out good. We'll choose one this time that's a real character. Let's do 1B19E. Okay, and what we're going to do is we're going to come to our chart here, and we're going to put that code in and say go. So I put in 1B19E. Now it tells me there's a new chart that contains the character, and there's an older one in the past when it used to perhaps be different. We use the current chart. Now, on this page, what we're looking for is 1B19E. 1B19, here it is. Go down that column to E. So it's this character right here, 1B19E. Don't know what it is, but the good thing about the Unicode character is if I ask you what that character was, following the characters themselves is a table which tells you what language it is, and if it has a special name, it gives it the name. So the one we're looking for, and I'll just do a find on it, was a 1B19E. You'll find it in the table, and then the second one will find it in the chart. So it's a Nushu character 1B19E. Don't know what it is, but that's its name. If, for example, the chart we were using, we cared about was ASCII. ASCII sits over here, basic Latin. And by the time we get down to its character names, we know a lot about them. So, for example, an exclamation point or exclamation mark has two other official names. One's factorial, the other is a bang. It says there's some other characters at these positions, like an inverted exclamation, a Latin retroflex, a double exclamation, an interrobang, a heavy exclamation mark ornament, that are characters in other places in the character sets. And so when you get to something like English where it has been well analyzed, you'll find that you can get a little better guide to which character you really should be using. Things like double quotes, you don't use just a standard double quote anymore. There's a leading one and there's a trailing one. One of the important things for that we'll see when we talk about the web, because they encode things slightly differently. But let's go back here and let's begin our encode. So first thing we said we want to do, look at your notes, see if you remember. The first thing we want to do is subtract 1, 0, 0, 0, 0. Now be careful with that, because remember this one is only 17 bits long. This 16 plus 1. The biggest number had another 1 in front of it. So you have to be careful when you use these smaller numbers that you realize you're not necessarily working any more than just slightly bigger than 16 bits. This has 17 bits because that is a 17th bit. So we have to do surrogate pair. That now leaves us with a Baker 19E, which looks like we could just encode it that way. The problem is there actually may be a character with that value, so we can't encode it directly. We do have to turn it into its two surrogate pairs. So first thing we have to do is we have to turn it into two 10-bit halves. Well, we don't have enough bits there. We only have 16 bits. So what we're going to have to do is we're going to have to make it 20 bits. So to make it 20, I add a 0 in front of it. Now we can write that out. 0, 0, 0, 0, B, which is 0, a 1, 9, and an echo. The split is right there. Now, once we split it, we need to put 6 more zeros in front of it. Oops. And then we need to regroup it from the right, so it's in sets of 4. Oops, I think I deleted something there. So now we have something that's going to be able to be added to our other values. The first one was D800, D800. Second one is D Charlie 0, 0. So adding those up, we get 1101, 1000, 0010, 1100. Adding this up, we get 1101, 1101, 1101, 1110. Now let's turn those into their nibble values in hex. Dog, 8, 2, Charlie. Dog, dog, 9, echo. So our values are D8, 2, Charlie, dog, dog, 9, echo. And if we were asked, that of course is the big Indian encoding in UTF-16. The little one would have to be 2 Charlie dog 8, 9 E dog dog. And we'd be done. Now you want to practice all these conversions so that you could do them. And also you want to be able to practice doing them the other direction. I haven't showed you the other direction, but those of you that are, on top of things will go, oh yeah, I would just have to do this to make that problem be solved in the other direction. For example, if I gave you this and told you it was UTF-16 big Indian, you should be able to give me back that. And same would be true. It's really simple if it's UTF-16 and you don't use surrogate pairs. Remember, this is a high surrogate. Oops, right here. That's the high surrogate. That's the low surrogate. In little Indian, that's the high surrogate. That's the low surrogate. So only the bytes flip within the 16 bits that we're dealing with. Okay, if that second example was helpful, give me a green light. Obviously, if I say to give me a green light and it wasn't helpful, give me the red light, right? Now, if I were you and I were in the class, you can be looking at the class list, not the chat, but at the class list. And as those things pop up, you can see who gave a green light, and then you can kind of look to see if they're willing to help you. You could text them or chat to get their text values and things. And I'm pretty sure in Blackboard, they have it set up so you can communicate among yourselves anyway, once you learn who, in quotes, the smart guys are. Not that, they're guys, and not that they're going to be more than all the class. They might be. But you want to make sure that you buddy up with people to learn these things and to practice these exercises. I now know that I made a couple mistakes in class last night when I was computing them. So you want to do these computations on your own and double check, and then we'll see on Monday if there was a problem. And these seems to match my values from last time I did these. So I'm pretty sure they're the right values. But last night I did one problem where I was off by a bit, and I have to explain that to the other class tomorrow night. Okay, so let's talk about the web. In particular, HTML5. If you're an HTML5er, and you should be, you're going to use a code called UTF-8. UTF-8 realizes that the web has an awful lot of old ASCII stuff out there. And because of that, why not make it so if you're sending ASCII, you're not penalized by the fact that we also want to, support Cherokee. And if you're in a language that is less used, maybe you're using some specialized piece of Greek where there's only a few scholars in the world that even know the language, then you probably could stand for more bits to be sent from your web pages because you're not making as much traffic as all the stuff that's out there currently written in ASCII. And wouldn't it be nice if all that ASCII could just automatically become UTF-8 by virtue of the fact that it is UTF-8? So here's the scheme for the compression in UTF-8. If a number starts with 0, and I'm in binary right now, and has 7 other bits in it that could be zeros or ones, these characters can always be sent as 1 byte and they're equivalent to, puts lots of equals there, ASCII. There's 128 possible characters that can go in there. They can be always sent as ASCII characters. So if somebody said, in UTF-8, how would I encode the letter K? What you would say is, well, K is the 11th letter of the alphabet. That's B in hex, right? Capital letter, so it's 4B. How would I write a 4B? Well, it starts with a 0. There's the 4-bit. Here's the B. And so this is ASCII for the letter K, and also is UTF-8 Unicode for the letter K. I simply knew it was the 11th character. I know J is 10, so K has to be 11. And I put it after the 4, because 4 is what I'm going to add to it until I get to 16. It stays a 4, then it flips over to a 5. And then I just simply observe the fact that I don't use the first bit anyway, so I can leave it a 0. So if it starts with a 0, it'll always be 8 bits long. It'll always contain 7 bits of good data. And there'll always be good ASCII. Now, what if I want to put 2 bytes out? Well, to say I have 2 bytes, I'm going to put 2 bits followed by a 0, and then I'm going to allow 5 bits of data. Second byte, which starts 1, 0, and allows 6 bits of data. 5 plus 6 means this can encode 11 bits of data. So as long as the code I'm wanting to encode will fit in 11 bits, using this encoding, notice it does not start with a 0. It starts with a 1, 1. Its continuation byte does not start with a 0. It starts with a 1. Both of these starting nibble, or shouldn't even call them nibbles, they're partial nibbles, always terminate with a 0. If the byte contains a 1, 0 as its starting character, it's always a continuation byte. If it has something else, it's always one that tells us how many bytes will follow. So using that as an encoding thing, I should be able to say, this is going to have 3 bytes. I'll have 4 bits that I could use here. Then I'm going to have I'll have 6 plus 6, which is 12, plus 4, which means I could encode 16-bit stuff, which we know there's an awful lot out there. Remember, UTF-16, other than using surrogate pairs, can always be encoded in 16 bits. So I know that I could fit it inside of 3 bytes instead of the 4 bytes that would be necessary if I use UTF-16. UTF-16 is required in Java because they don't support UTF-8 directly as their character set. They do support UTF-16. So I can store 16 bits. Well, let's go one more. 3 bits here. How many do I have now? I have 6 times 3, which is 18, 19, 20, 21. Well, that's convenient. I can store anything that's up to 21 bits in 1, 2, 3, 4 bytes. So let's do one. Let's take our number we had a second ago and deal with it. What was it? It was, well, let's use this one. We know that's 21 bits long. Let's first of all write it out in binary. Okay, we know there's 4, 8, 12, 16, 20 bits by the time we get here. There's 21. So we'll just get rid of the first 3 because we know we don't need them. There's 21 bits. Now, using this last pattern, I'm going to write underneath it. What we're going to do is we're going to take these 21 bits. Normally, I start at the right and work to the left, but since I know I have exactly 21 bits down here, I can just encode them. So I have 1 followed by 4 zeros. We'll come back and fill in the rest of it. I have 4 ones, 4 more ones, 4 more ones, and 4 ones. So this would be a 1, 0. This would be a 1, 0. This would be a 1, 0. So in order to encode this number in UTF-8, I need all 21 bits. And the value I get after everything is plugged in is right here, right here. So let's write that out in 8-bit entities. F4, 8F, BF, BF. UTF-8 is always 8-bit entities, so there's no little indent or big indent. It's always 1 byte, followed by another byte, followed by another byte, followed by another byte. These are unambiguous in the stream, meaning that the starting part always tells you, if it's a byte that says there's going to be some bytes continuing, how many bytes there are by just counting the ones. And any continuation byte always starts 1, 0. If, however, it started with a 0, it could never be confused with any of those, and then it can be encoded in a single byte. The other good thing this has is it's kind of self-correcting. If you make an error, you can keep scanning characters until you find another one of these starting group things, or until you find an ASCII character. So let's code our other number that we were working on there. What was it again? I wrote it down. 1B19E. Actually, I'm gonna make it a little bit easier. I'm gonna get rid of the starting 1 just to show you something else. Let's pretend like we had a character E19E. How would we find out if we actually had that character, if that was a valid character? Well, we could go to our charts. We go to the top and plug it in. E19E. Because there's a chart containing it. We can go there, and it says this is a private use area, meaning that there is no assigned character, but if you're a large corporation, internally need special characters. For instance, you have your own encoding for something you do within your company. You can put your own characters in here. For example, I imagine the Coca-Cola company has encoded all of the letters that are in that signature Coke sign, not the Coke, but the Coca-Cola sign. And so they would have a private area. Our private area still would need to be encodable. So let's go ahead and do the encoding. How do we encode it? Well, we're going to need to write it out in bits, first of all, and see how many, well, we can count the bits here, but let's write it out in bits first. E, a 1, a 9, and an E. Looks like we got bits all the way over here, which means we have 16 bits. So the encoding we're going to use has to hold 16 bits. Do we have an encoding that will hold 16? Well, 21 would, but this one will too. Let's use this encoding because it's smaller. This one won't hold it. So let's grab this. Let's write it down here. Now what we need to know is we need to shovel these numbers underneath the values here. So let me put some spaces in so I've got something to do with. So those 4 right there go here. Those 2 right there go here. This guy. Oops, I don't want to cut him. He goes there. These 4 go there. Those 2 go here. There's the 1, 0 comes down. And then we have 4 more to go. And that comes down. So what is our value now going to look like? It's going to be E, 8, 6, 9, E. So this is the UTF-8 encoding of that hex code point. This is a code point. This is an encoding. This is an encoding. This is an encoding. This is a code point. Code point can be encoded many ways. So when we would be working, this is a code point. So if I had given you this encoding, wherever it was down here, I guess it's this guy right here. If I'd given you this encoding, you'd be able to turn it back into this code point. And all this really is how far into the Unicode table is it? That's a number, right? And you just count 0, 1, 2, 3, 4, 5 until you get to this huge 21-bit number. And that's the biggest code point that can be in the table. Okay, I'm going to move on to another topic. Temporarily here. Let me see if I have it open on my screen. I probably do. Okay, we're going to need to know some things about electricity. And we're going to have to, after next class, certainly be able to do some simple design of some circuits containing minimally resistors and possibly some light-emitting diodes. But for our circuits, there's 3 or 4 main things that we're going to have to worry about. We're going to have to worry about something called voltage. We're going to have to worry about something called current. We're going to have to worry about something called resistance and something called power. And those are going to be the main concepts. Now, some of you have probably had this before, and you may have had it in different venues. You may have had it in a physics setting, and some of the things I'm going to say may disturb you a little bit because I'm not going to stick exactly to some of the physics definitions. It's like vectors. There's 3 people that actually consume vectors. There's physicists, there's mathematicians, there's computer scientists. And they all 3 have totally different definitions of what a vector is and how it's used. And yet each can use the others and share in what it is while believing it's something else and still being kind of offended by the fact we did it that way. So in this case, I'm going to give you a kind of the standard way if you were an electrical engineer, you'd be looking at these things. Not if you were a physicist and not if you were a casual, trying to write science fiction type of a guy. So what we're going to talk about, first of all, is the relationship among some of these things and the measurement quantities. Voltage is going to be, let me actually put it up next to it, even though the ordering here will be inconsistent. It's going to be measuring volts, which we'll use the unit V to describe. And we can think of voltage as a pressure. Now, that could be disturbing to some of you, but the idea is that voltage doesn't move. It's simply an existing pressure. So expressions like the voltage went from here to there don't make any sense because voltage doesn't move. Voltage is always a relative thing. It's the pressure of something relative to some other spot. So if I touch the other spot with a meter and this spot, I should measure a difference in pressure or no difference in pressure. And I could describe that by saying there's a certain amount of voltage across that particular component or between these 2 spots in a circuit. Now, there's kind of a generic measurement called ground, which is often thought of as 0 volts relative to something. And we can generally kind of wave our hands around and talk about it being the point against which we're measuring. We may let that slide sometimes, and other times we won't. You'll see why later. So voltage is an important quantity, and we're going to see that it has a linear relationship in terms of its definition that we're going to make use of. Current, on the other hand, does move. Current, think electrons, and then don't think electrons. We're going to invent something called conventional current. And yeah, I know it's really electrons that are moving in your circuit, but we don't care. We're going to pretend like there's something moving in the opposite direction. with exactly the same mass and energy and all those other things, the same charge that an electron would have. And that'll make us consistent with all the colleges and with all of the electronics people that we're going to encounter that are going to be approaching circuits from the way we are. There'll be a time to think about electrons, but it just isn't now. And by just imagining it, now you can kind of also think of that. I don't know if you've ever sat in a train station, like go to Penn Station in New York and sit in the train, and then have the train next to you start moving while you look out the window. You won't know if you're moving or that train is moving. It'd take a couple seconds before you to figure it out. Same is true with us accepting conventional current to be something. We can blame Ben Franklin. Wasn't all his fault, though. There's good reasons for us to think of it this way. We're going to measure in amperes, A-M-P-E-R-E-S. But we'll probably almost always call them amps. And we'll very rarely be working in whole amps. Often we'll be working in thousandths of an amp or millionths of an amp. But amps is the main unit for which around which the functions we use will be dealing. Resistance we can think of as a pipe which has a smaller circumference or a larger circumference, and the amount of circumference it has will dictate how much, for example, water could get through it if we were pushing on it. Or we could think conventional current could get through it if we were giving a voltage pressure against it. So resistance is going to be measured in ohms, and the signal for, or the symbol for that is a Greek letter, capital omega. And I can't type that in this editor, so I'll just tell you that's what it's going to be. And if I just say ohms, you'll know that that's the symbol we're using. Resistance, again, very often will be measured in hundreds of ohms or thousandths of ohms or even 10,000ths of ohms when we're building circuits. But nevertheless, we can relate these with something called Ohm's law. Ohm is a person, so we can put apostrophe S. What we're going to say is the voltage in volts is equal to the resistance in ohms times the current, which we measure as using the letter I, because A was used up, in amperes. So there's a linear relationship. So that also means, you know, that R is equal to V divided by I, and that I is equal to V divided by R. So all those are true. We just rearrange the algebra. And we might be given any two and have to determine what the third one is. I'll show you a little later, maybe not tonight, but on a different time, a quick, easy kind of cheating way to remember all that formula. But Ohm's law is fairly profound. The important thing here is that it's linear. We don't have any squared terms. We don't have any logarithmic or exponential terms to deal with. So the math is going to be easy. Now, in a simple circuit, if we just simply put a battery which can generate voltage and can supply current in the circuit, and we connect to the two ends of a battery through a resistor, we're not really going to do much work, but the work we do, we can think of as power. And we can say that the power we're going to generate, in our case might just be heat, is equal to the current times the voltage. And I just give you that as just the definition. So the power measured in watts or milliwatts or microwatts, so it might be thousandths or millions of a watt, and will be abbreviated with the Greek or with just the letter W when we use it in an expression. So P stands for power, it's measured in watts, which are W. I stands for current, which is amperes measured, we use an A. Voltage is V. So let's look at a simple circuit and think about how this all might apply to it. Now, unfortunately, the computer I have has a pad on it, which would allow me to write. Unfortunately, the pad doesn't work with this computer. So I'm going to have to use my mouse, and don't expect my handwriting to be the world's best thing that you've ever seen. It will not be. I'll let that stand for now and open that. Okay. I'm just going to start with a simple circuit. This symbol right here is a battery. It's a source of voltage, source of current. It has a plus end on the end that has the higher voltage potential. It also has the longer line on that end. That end on a battery is called the cathode. Now we'll see later the cathode is usually the negative end of everything else, but on a battery the cathode is the positive end. The negative end of a battery is called the anode. Now the large small line convention stands for a battery cell, but in our world we're not going to keep track of the voltage that way. We're going to simply state the voltage to the side. Normally in batteries this would be in 1.5 volts plus 1.5 volts would be 3 volts, or it might be 1.2 and 1.2, which is 2.4. So we generally don't do that anymore. We also have indicated a ground potential. The ground potential here conceptually is a place where if we touch a probe here, we're going to think about it as being 0 volts relative to someplace else on Earth or on Mars. We don't care. But we'll measure everything in this particular circuit relative to ground unless we're looking at a particular other reference point. So if I hooked a meter touching here and a meter touching there, I would measure whatever voltage this particular battery is producing. It's an increasing voltage because the high end of the battery is here. So if I gave this battery some voltage, let's get creative by using draw. I don't think I can bump this up though when I'm drawing, unfortunately. Let's say this battery had 10 volts across it. What I'm saying is if I measured the battery from one side to the other, there's a 10 volt difference. If this ground were not considered 0, this could be any voltage relative to whatever this was. So if this were 10 volts and there's a 10 volt rise, this would be 20 volts. So voltage is relative. When it's relative to 0, of course, it's easy to say that this point right here is also 10 volts. This point right here is 10 volts lower, so it's 0 volts. Now, if I took a wire and I hooked the top of the battery to the bottom of the battery would instantly conduct infinite current. It would heat up, blow up, we'd all fall into a black hole and we'd die. Well, fortunately for us, this is a real battery, not a theoretical battery. So the battery itself would just drain quickly and get hot. When we talk about the battery in a circuit here, we're not talking about a real world battery. We're talking about an ideal battery. The ideal battery has no internal resistance. Real life batteries do, and it affects their output. We're going to pretend like we're in the imaginary world for now. And so this is an ideal world situation where this battery really says it can produce 10 volts. It always will, unless we connect the top to the bottom, in which case it would be impossible to do that because 10 volts and 0 volts could not be equal. So in order to keep this from having that situation, we hook a resistor from the top of the battery to the bottom of the battery. And this resistor will have some value in ohms, which will help us determine how much conventional current flows in the circuit. Now, for our purposes, this entire wire to the top of the resistor has exactly the same voltage everywhere. The voltage here from the bottom of the battery to ground all the way to the bottom of the resistor has the same voltage everywhere. This voltage and that voltage will be regulated by the amount of resistance here. We already said this can't be 0 volts because that would cause a short circuit. So if it has some amount of resistance, some voltage has to drop across it. Well, how much will drop? Well, it's dependent upon the Ohm's law. Let's assume that there was 10 ohms as the resistor. If I have 10 ohms and I have 10 volts, let's go solve for the current. I need to solve for current, so I need to take the voltage and divide it by the resistance. So I is going to equal 10 divided by 10, so it was 10 volts divided by, 10 ohms. What's that going to give us? 10 divided by 10 is going to give us 1 ampere. So if we look at this circuit, we know that there is flowing through the wire, through the resistor, and back to the battery, the same 1 amps. We know that at the top of the resistor, we have 10 volts if we were to measure it relative to ground. And if I just say 10 volts, I always mean relative to ground. And we have ground at the bottom. So we know that the drop across this, if we were to look at the voltage drop across this resistor, there has to be a 10 volt drop because all of the drop has to occur to get back to 0. Now, there are a couple other laws that we will look at and think about. One is called Kirchhoff or Kirchhoff's, depending on where you are, and sometimes it has 2 H's, sometimes it doesn't. Voltage law, which says around a loop in a circuit, the sum of the voltages equals 0. So basically, if we add 10 volts somewhere else in the circuit, in order to get back to 0 volts here, we have to lose 10 volts. So this is a 10 volt rise. This is a 10 volt drop across the component. It adds up to 0. Notice this is a single loop. If there were multiple loops, that would hold true of all of the loops. But in our case right now, that simply means that we can compute what the current going through the circuit has to be. Now let's see if the eraser on this works reasonably well. I'll try to get the touchpad working, and if I can get it working, then writing these things is simpler. Okay, let's say that for whatever reason, oh, and we didn't finish the rest of that problem, did we? We also need to compute the power. The power is going to be equal to the current we had, which was 1 amp, times the voltage, which was 10 volts in that particular resistor. So that resistor then has got a 10 watt voltage drop across it. 10 watt resistor is a big resistor. So if you use a small one, it gets hot, okay? 10 watt heater, okay? Now, we obviously, in a very regular circuit that would be used with a computer, may draw this much for the whole system, but chances are pretty good we're not going to be drawing that much for any individual component. We computed in the circuit the power across this resistor. How much did it use? There also was a power gain here, but this was a power loss here. Okay, so let's assume that for the problem we needed to have, let me get my pencil again here. Going through the circuit, we needed to have 5 amps. And the resistor we had when we looked at it over here had on it that it was a 100 ohm resistor. What size battery do we need to get, or what size power supply do we need in order to make that happen? Try to work that out by yourself real quick. Here's a great case where your grocery store calculator comes into play. So our formula we need is V is equal to I, which we know, times R, which we know. So let's take I, which is 5, multiply it times R, and we see we need a 500 volt power supply. which means 500 volts rises in the battery. If 5 amps are being produced, 500 volts drop across the 100 ohm resistor back to zero. How many watts are we going to be burning in this? Oops, didn't mean to do that. Well, the power equation, power in watts, is equal to the current in amps times the voltage in volts. So basically multiply those two together. So using our grocery store calculator, we can just take the number we have times 5. So we'd be producing 2,500 watts. Now, as the good engineers we are, we actually wouldn't specify it that way. What we do instead is, as engineers, we always make sure that there are 1, 2, or 3 digits in our component part that we're going to be talking about. And we always move the decimal point around in such a way that we can have 1, 2, or 3 of those digits in front of the decimal point. So in this case, I could put 25.00, or I could put 2.500. I could put 0.2500. Well, it turns out that we always move the decimal point so that we're going to get a value which can be a multiple of 3. This guy we moved the decimal point to, so he's no good. This guy we moved it 3 positions. He's okay. This guy we moved it 4. He's no good. So what we're going to do is we're going to take and say 2.5 something watts. And the something we're going to use as an engineer comes from our prefix table. And let me find my browser again. The prefix table looks like this. Normally, we're in between 3 and -3. Units without a prefix go right in there, meaning that I have a 10 of 1 of something, 10 of something, 100 of something. If I go to 1,000 of something, move it 3 positions, I say kilo. So in our thing over here we were working on, this would be kilowatts, 2.5 kilowatts. Lowercase k, uppercase k, sometimes we're going to find, and I may or may not teach it in this class, that there's a set of prefixes that have to do with powers of 2 as well, which are, instead of 1,000, you multiply things by 1024. They're more precise with computer processing, so we may talk about them, but in general, engineers use regular standard prefixes like these. If I'd had to move it 6 positions, I would have used mega. I would use giga if I moved it 9. If I had to move it the other way 3 positions, I use micro, which is the Greek symbol, the lowercase micro. N for nano, pico, femto. I always thought it'd be cool to have 2 kids and name one Yato and one Yachto. But I named them something else. I think I named them true and false. I don't remember anymore. Okay, so this is the prefixes we'll use. So the rules are a little tricky getting used to them. For example, if I had something and it said 200, is that number already correct for what we need? Well, it's 3 digits to the right of it or to the left of a decimal point. So that would be a legitimate answer. How about the number 22 for that number? What should that actually be? Well, if I move it 3 positions, the decimal point will be here. That's legal, right? If I move it 6, the decimal point will be there. Let's move it 6. 6 doesn't really work because there's no digits to the left of the point. There should be 1, 2, or 3 digits. And the digits to the left need to be significant digits. In the number 200 here, if there's a decimal point here, we don't know if those digits are the result of something being rounded or if they were the actual measurement. Maybe we measured exactly 20 point something and there's two significant digits here. So in another class,